by coloring in the appropriate outcome that we're going to cover today. So I need you on page 2 in your notes booklet, and I'll have you grab a green highlighter, or if somebody wants to pass out the green highlighters, you can take a green highlighter. And what we're looking at here, there's only one outcome that we're covering today, but it's kind of a big one. We're going to explain qualitatively static and kinetic forces of friction acting on an object. So we're looking specifically at force of friction today, but after we're done dealing with force of friction, an outcome we've already colored is calculate the resultant force acting on an object by adding vector components graphically and algebraically. That's going to be green as well. I think we already colored that one. And apply Newton's laws of motion to solve algebraically linear motion problems in horizontal and vertical planes near the surface of the Earth, ignoring air resistance. And that's going to be green. When you're finished coloring that, can you put the highlighters back in the jar, and I'll get Grandpa O to collect them and put them back on the table where they came from. When you color those outcomes, then you can, in your notes booklet, I need you to be on page, there we are, we're on page 19. Okay, force of friction is what we're talking about. Okay, when non-smooth surfaces come into contact with each other, they oppose, and this is friction. It's actually due to the friction occurs as a result of the electrostatic attractive forces that are between two surfaces. The two surfaces will always generate some friction, and friction always opposes motion. And this is because at the microscopic level, all surfaces, even really shiny, smooth, glossy surfaces, they all have some roughness to them. There actually exist bumps on the surface. And when those surfaces rub together, they slide together. Let me see if I can do a little animation here. So if we take these surfaces, and when they rub together, right, when one surface rubs over another surface like that, it actually, those little bumps, they rub against each other, and that is what causes friction. So when we also only experience friction when something is on a horizontal surface. So it will have a gravitational force acting down on it and a normal force acting up on it. We usually have some applied force trying to move it forward against whatever that force of friction is. It opposes the motion, right? Because friction opposes motion. So friction will always be in the opposite direction of motion. Okay, the nature of those two surfaces, like how much friction there actually is between two surfaces, is expressed as something called the coefficient of friction. And the coefficient of friction is symbolized with this funny shaped U, and that's called mu. That's the sound a cat makes if you can say it fast. So it's mu. This number is always less than 1. It's a ratio, really, that indicates the amount of friction between two surfaces. Okay? And we're actually going to find that there's two types of friction. There's static friction and there's kinetic friction, but a little bit more about that in a minute. The value of mu depends only on the nature of the two surfaces, not on the surface area. And there was an activity during the Newton stations investigation where you had the block of wood, and it asked you to pull it flat on its flat surface, like on the larger surface, and see how much force it required to pull it, and then to turn it up so it was on its smaller edge and see how much force it required to pull it. The forces should have been the same because there was no difference in the amount of friction acting on that piece of wood. Okay, so the value of mu depends on the nature of the two surfaces only, not on the surface area of contact. It doesn't matter how much of the object is touching, it's just the type of surface. The formula for the force of friction, Ff, is mu Fn. And as long as we're on a horizontal surface, Fn equals Fg. And so the force of friction, the formula is actually mu mg. I repeat that. When an object is on a horizontal surface, the normal force is equal to the force due to gravity acting on the object to the weight of the object. So down here is where we wanted to have Ff equals mu mg. So Ff is your force of friction in newtons. Mu is the coefficient of friction. There are no units for that. And Fn is your normal force in newtons. And remember that when an object is on a horizontal surface, the normal force exactly opposes force of gravity, and so they are equal. Okay, so when we talk about friction, there are two different kinds of friction. There's static friction and there's kinetic friction. Static friction is for stationary objects. So static friction has to be overcome in order for an object to move. So if the applied force is not bigger than the force of static friction, the object won't go anywhere. But if the applied force is big enough, then the object will move. So it requires a larger F applied to get an object moving. The coefficient of static friction is mu with a little f, and that represents the conditions just as the object starts to move. So we can actually specifically state our force of friction as force of static friction is equal to mu f times Fn. The other type of friction is kinetic friction, and it's for sliding or moving objects. It's lower than static friction. Since an object is easier to move once it's already moving. So you need to apply a much larger F applied to get an object moving to overcome static friction. Once you've overcome static friction, you don't need to apply as large of a force to keep it in motion. So it requires a smaller F applied. And then for a formula, we can then write Ff kinetic equals mu k times Fn. And what we usually have is that mu s is greater than mu k, right? So the coefficient of static friction is always larger than the coefficient of kinetic friction. The force of static friction is always larger than the force of kinetic friction. And we can represent this on a graph. We have here force due to friction versus applied force. And so what happens there is you have to apply a larger and larger force in order to overcome the force of friction. And you're going to hit some point up here, which corresponds to the force of static friction. And once you reach that force of static friction, it actually requires a smaller force. It requires a smaller amount of force in order to overcome, or to keep that object moving. Mu, in our formula where we have Ff equals mu Fn, which is mu Fg, what that actually shows you is that mu is just the ratio of force of friction divided by the force of gravity. So if you were to make a graph of the force of friction versus the force of gravity, you could find mu by finding the slope of that particular graph. We're not going to do that though. What we want to do now is just some examples using force of friction. So what we actually have happening here is we have, let's remind you of some of the formulas that we have to work with. We have F net equals mass times acceleration. We have Fg equals mass times acceleration due to gravity. And now we have Ff equals mu mg. So mu times the force of gravity. So now when we're finding net force, we make our free body diagram, we have an extra formula now. We're not just solving for force of friction or plugging in a value for force of friction. We're actually might be solving for mu or for mass or something like that, or using mu to find the force of friction. So we'll start easy. A 14-kilogram object is resting on a horizontal surface. What is the normal force acting on the object? So this is just to remind you that normal force, when you have something on a horizontal surface, the normal force is just equal to the force of gravity. So Fn equals Fg, which equals mg. So 14.0 kilograms times 9.81 meters per second squared. And you should get 137 newtons, and it's the normal force, so the direction of that normal force is up. Okay, just giving you guys some time to catch up there, and then we'll do example 2. Okay, a horizontal force of 65 newtons is required to pull a 10-kilogram block of aluminum at a uniform velocity across a horizontal wooden deck. What is the coefficient of friction? Uniform velocity, that means there's no acceleration. So that means F net equals 0. So when we draw our free body diagram, we draw our free body diagram. We have Fg acting down, Fn acting up, applied force forward, and if there is no net force, then that means that the force of friction acting backwards is exactly equal to the applied force. So we still have to write out F net equals F applied plus Ff, but because this equals F net equals 0, then we can cross that out, and what we have then is that Ff equals F applied. And remember, Ff would actually be negative, but then that means we're going to add it to both sides so we can dispense with the negative. Then we have mu mg equals F applied. So mu is equal to F applied divided by m times g. So 65 newtons divided by brackets. You want to be really careful with your brackets the time you plug these in. 10.1 kilograms times 9.81 meters per second squared. And we want bigger brackets there on the bottom because you want to go 65 divided by whatever 10.1 times 9.81 is. And you should get a number less than 1, 0.656. Remember, there's no units. If you don't get a number less than 1, then check how you put it in your calculator, because that probably means you didn't bracket the denominator. Okay, example 3. A 9.8 kilogram object is pulled along a horizontal surface. If the coefficient of friction is 0.18, how much horizontal force is needed to pull the mass across the surface at a constant velocity? So again, we have a constant velocity, which means F net equals 0. So we have Fg acting down, Fn acting up. We have an F applied forward, and Ff is the same length backward. F net equals F applied plus Ff. F net is 0. So then F applied equals Ff. So F applied equals mu times m times g, which is 0.18 times 9.8 kilograms times 9.81 meters per second squared, which should give you 17 newtons. And if you get a positive answer, so I forgot my directional justification there, positive for forward, negative for backward, then that's 17 newtons forward. The friction would have normally been negative, but since we're adding to both sides, we're using algebra to move the F side over, then we can dispense with the negative. If you need more time to fill in the examples than I'm giving you in the video, please pause the video. That's the easiest thing to do. Okay, so on to example 4. A cart with a mass of 3.1 kilograms is pulled across a level depth by a horizontal force of 9.5 newtons. If the coefficient of kinetic friction is 0.14, what is the acceleration of the cart? So now we have some acceleration. So we're going to do forward positive, backward negative. We have our free body diagram. We have Fg acting down, Fn acting up. F applied is forward, and we have a smaller force of friction acting backward. So we have F net equals F applied plus Ff. So in this step, we'll fill in what formulas we know. So F net is mass times acceleration. F applied is just a force that we're given, plus mu times m times g. So acceleration equals F applied plus mu times m times g divided by mass, which is 9.5 newtons plus 0.14 times 3.1 kilograms times negative 9.81 meters per second squared. And I'm not making gravity negative because gravity acts down. I'm making gravity negative because my friction is negative because it's backwards. And the easiest way to make that negative is just to make gravity negative. Divide that then by 3.1 kilograms And you should get an acceleration, I'm just going to write it up here, of 1.7 meters per second squared forward. Okay, example 5. A 9.5 kilogram box is pulled across a level floor where the coefficient of kinetic friction is 0.32. What horizontal force is required for an acceleration of 2.2 meters per second? So similar in setup to the previous question, except that what we're solving for is different. So again, we have Fg acting down, Fn acting up. We have an applied force forward, and a force of friction acting backwards. F net is F applied plus Ff. So F applied is going to be F net, which is mass times acceleration, minus Ff, which is mu mg. So this minus here, the minus mu mg, that's the minus from algebra. We still have to make friction negative when we plug in our numbers for it. So our mass is 9.5 kilograms times 2.2 meters per second squared minus 0.32 times 9.5 kilograms times negative 9.81 meters per second squared. Okay, and that should give us our applied force, and it should be a positive number because we're minusing a minus, which means we're adding, and you should get 51 newtons forward. Okay, in example 6. A 75 kilogram hockey player coasts along the ice on steel skates. If the coefficient of kinetic friction is 0.10 or 0.010, what is the force of friction? So that's just finding force of friction. Ff equals mu mg. So 0.010 times 75 kilograms times 9.81 meters per second squared. And if we're just finding the force, we're not dealing with directional justification yet. We'll just put down what force we got, which is 7.35 or 7.4 newtons, and that's going to be backwards. Now, in the next part here, we're going to have to do a little bit of calculating. We want to know how long will it take him to coast to a stop if he's traveling at 1.2 meters per second. So VI is 1.2 meters per second. VF is 0 meters per second. We're looking to solve for time. But in order to find time, because we're going to use this formula, acceleration is VF minus VI over delta T. So delta T is VF minus VI over acceleration. So I'll move this one down here. We need to find what our acceleration is. So we also have to find acceleration. So we're going to do a step first here. So this is our first step, and then we'll move over here. So what we have to do is find the net force, so then we can find the acceleration. Whoops, I've drawn my three-body diagram wrong. We have an object that's slowing down mainly just due to the force of friction. So that's the only force we have acting on that object besides the balance, force of gravity, and normal force. It's only forward positive and backward negative. So we have F net equals Ff. And we found Ff already, so acceleration is going to be Ff over mass, which will be negative 7.35 newtons divided by the mass of the hockey player, who is 75 kilograms. Okay, so that will give us a negative acceleration, negative 0.0981 meters per second squared. So we can take that number and plug it into our formula over here. So we have 0 meters per second minus 1.2 meters per second divided by negative 0.0981 meters per second squared, which gives us a time to stop of 12 seconds. And that answers that question. Okay, so hopefully you were able to stop and start through that so that you got everything written down. And the assignment, what I want you to work on now, is going to be in your practice booklet. And it's page 15 to 18, 1 to 12. Okay, have a good day, guys. I will see you on Tuesday.